today she will be talking to us about probing accretion via X-ray spectral timing. Thank you very much.
Thank you.
I'll keep an eye on the chat, and if there's any questions, I will let you know so you don't have to keep an eye on it.
Okay. Good morning. Thanks for having me here today. So during this talk, I would like to entertain you discussing black hole accretion and how we can approach a few problems about accreting black holes using X-ray spectral timing techniques, which are basically techniques that use both the spectral and timing information to study these systems. So here is a outline of the talk. So I will be first introducing the complex phenomenology that characterizes these systems. I will focus on stellar mass black holes because they are ideal laboratories for this kind of studies, because they allow us to see all different accretion states in the same source during the human time scales. But bear in mind that many of these problems maybe translate to supermassive black holes as well. And also these techniques can be used on supermassive black holes. And I will give some examples. And then I will discuss the problem. I will be focusing on the problem of constraining the geometry of the innermost accretion flow in these systems. I will discuss why this is important, what's the state of the art of the observations, and discuss a bit the models. And then I will discuss spectral timing study that we performed on the source MAXI J1820, which is a black hole binary system, a famous one actually, and how we use this technique to constrain the evolution of the geometry of the accretion flow during its outburst. Okay, so astrophysical black hole systems are very interesting systems. They have a lot of peculiar properties, but the properties that interest us the most are the fact that they are powerful X-ray emitters, and this emission that is observed, and these allow us to actually observe them and study. And this emission is not only powerful, but shows incredibly strong variability phenomenon. So basically, we can see these flux varying on a wide range of time scales. This range of time scales depends on the mass of the black hole. And for stellar mass black holes, we can see variability over days to months time scale, which is the time scale of an outburst, as we will see, down to milliseconds or even shorter time scales. So go on. Okay. So before going into the details of this, studying the geometry of this system, I will give you some brief introduction on which are the main spectral ingredients that allow us to study this system. So basically, this is an example of an X-ray spectrum of a black hole binary. So as you see, it shows several features. So the main component in the spectrum is this thermal component. Basically, it is due to the fact that the black hole accretes mass. This mass forms an accretion disk, and the matter going to the black hole in this accretion disk is heated up to very high temperatures, and it emits locally as a black body. The sum of this black body, spectra, forms this feature here that is a multi-temperature black body spectral feature. And so this is the primary engine that powers this system, but there are a lot of open questions regarding this engine. For example, one of the most important ones is how close this disk can reach down to the black hole, and how this configuration evolves as a function of accretion state. So this is an important question because depending on how close matter can reach down to the black hole, we can measure or not the black hole spin. So only if we have matter very close to the black hole, we are sensitive to spin measurements. So as you see, this is not the only component that we need to describe the spectra. There is also a hard X-ray tail. And this is a very important component because it represents, it contributes a lot to this spectrum. And basically, this can be explained, this hard X-ray component can be explained in terms of Compton upscattered emission in an optically thin region, which is located close to the black hole. So this is made up of hot electrons and produces this hard X-ray component by Compton upscattering the thermal photons from the disk. However, we don't know much about this region. We don't know how it is powered, what is its geometry, whether it is like an atmosphere covering the inner parts of the disk, or like a cloud, or maybe, as we will see, the base of a jet. And moreover, we don't know how it changes as a function of accretion state. And then, as I mentioned, there are jets. So jets are powerful outflows of plasma. So jets are emitted. So these are very important components in this feature, in these systems. There is a debate whether or not they have a significant emission, they give significant contribution or not in the X-ray band, but for sure, most of their contribution goes into the infrared. And these jets are observed during some accretion states in this source. However, there is a lot of mystery around the production mechanism. So what are the conditions for the jet to be launched? And how is it linked to the hard X-ray source, so this hard X-ray emitting region? So now I will go through the phenomenology that we observe in this system from a spectral and a timing point of view. So black hole binaries are usually not observed, so they are very dim. They spend most of their time in a quiescent state, which means that they are barely or not observable in the X-ray. However, they undergo outbursts of activity from time to time. And when this happens, they can change their luminosity by several orders of magnitudes. So during an outburst, they undergo a complex evolution of both the spectral and timing properties. And we can sort of summarize this evolution using this kind of plots here, where we plot the intensity of the emission, of the X-ray emission as a function of hardness, which is like the ratio between two X-ray bands. And as you see, the source spans a large range in luminosity and in hardness. So during an outburst, the source evolves through different states, following a well-defined pattern, moving into this diagram in an anti-clockwise direction. But we can define, so there are many states here, but we can define two main states. So the hard state and the soft state. They're called like that based on the spectral properties of the source in these states. So in the hard state, the spectrum is dominated by this hard X-ray comptonization component, which contributes, which dominates above 1 keV. While in the soft state, the hard comptonization component dims, and the spectrum, the X-ray spectrum, is dominated by the thermal emission from the disk. We also see a jet in these systems, but the jet is not observed in all of the states. The jet is observed mostly in the hard state, where it's steady and unresolved. While in the soft state, the jet sort of disappears. It looks like it's quenched, so it's not clear whether it just dims or is totally suppressed. And this the disappearance of a jet happens when crossing this line. So there are also many interesting timing properties, so variability properties of this source. These are, during an outburst, these properties change dramatically. And this plot here sort of summarizes these changes. It's a plot of power, it's a power spectrum basically. So it's how the variability power is distributed over frequencies of variability, temporal frequencies, as a function of for different accretion states. So in the hard state, we observe strong variability on short time scales. And this is shown here. The power spectrum is very strong. So this characterizes all the hard state. But when we are up in the bright phases of the hard state, discrete features like the quasi-periodic oscillation can appear. They are observed in many sources, and they appear mostly in this part of the diagram. And they, so these are quasi-periodicities in the light curve, in the X-ray light curves of these sources. When the source gets into the soft state, the variability drops. So there is very weak or undetected X-ray variability. So an important phase of the outburst is this transition here, because in this phase of the outburst, we see dramatic changes. We see dramatic changes in the spectral properties. We see this drop of variability, and we see the disappearance of a jet. So this disappearance of a jet happens through a phase where the steady jet is not observed anymore, but radio flares are observed, and these radio flares are associated to ballistic jet ejections that are observed mostly in the radio, but they have been observed also in the X-rays with Chandra. And these jet ejections are emitted at velocities close to the speed of light. So just to draw a parallel with AGN, as I told you, yes, I'm discussing stellar mass black holes, but many of the properties that we observe in stellar mass black holes are observed also in AGN, but not in single sources. Like to observe the wealth of properties that we observe in a stellar mass black hole, in a single stellar mass black hole system, we should observe many classes of AGN to draw a parallel. So, for example, we know that there exist jetted and non-jetted AGN. So these sources show many similarities. The time scales, however, are very different. So as I said, the time scale should scale with the black hole mass. So if we want to observe transitions or an outburst evolution in AGN, this is not doable because the time scales, if this happens, this would happen on very long time scales of the order of a factor 10 to the 5 longer time scales. So basically, we don't know whether AGN make this transition that we observe in black hole binaries, although there are some candidates for this. Okay, so the question now is, how can we explain this complex behavior that we observe? So there are several models that try to explain this evolution. We can, basically the main class of models that is pretty much successful in understanding some of these states is the class of truncated disk models. So according to these models, when the source is low in the outburst, so it's either in quiescence or in a low hard state, the disk is the optically thick, geometrically thin accretion disk is truncated to large radii, and is replaced by an inefficiently accreting flow in the inner parts. So this would explain why the source is very dim in these phases, and why we are dominated by this hard X-ray component. However, so in the soft state, these models postulate that the disk can reach down to the innermost stable circular orbit or close to it. So the disk now is very powerful and should dominate the energy budget. And the hard X-ray source is instead less dominant. So it's made of maybe smaller regions. Okay, so now the question is, what are the observational evidences for these models? So people are very much convinced that these models can work when the source is in quiescence or low in the hard state, and when the source is in the soft state. So this is because we have observational evidences for this. So this is one of those examples of observation that prove this scenario. So basically, this is one famous system that I think it goes into outburst. Well, it went into an outburst, I think 80 years ago, and then 70 years after. So it was regularly monitored, and by chance, people could observe the source just 13 hours before the start of the outburst. So basically, they could see how the optical spectrum changed. And what they saw is that this H-alpha emission line from the accretion disk got broader. So by measuring the broadening of this line, it was possible to estimate a radius of emission. And what they found is that this radius evolved from a large truncation radius down to a smaller truncation radius. So this was taken as an evidence, a clear evidence that the disk is highly truncated when the source starts an outburst. Another evidence comes from the study of the broadband continuum. In some sources, it was possible to measure the thermal disk emission in these low states, and the disk appears very dim and cold, which means that it must be located very far from the black hole. In the soft state, instead, the disk dominates the spectrum. And what it is observed that, the disk is consistent with being close to the black hole, so at the innermost stable circular orbit. But what is interesting is that despite these changes in luminosity of about 1 order of magnitude, the emitting area remains constant. So it looks like the source has reached some sort of stable configuration. Now the questions are, what happens in between? So how does the source evolve from this state to this state? So many of the questions about black hole binaries, this evolution, this outburst evolution, are related to what happens in between this quiescent and the soft state. So what happens in the hard state and at the transition. So basically, one of the main questions is, how do we explain the hard state, and when does the disk reaches the innermost stable circular orbit? Now, these models here are very popular. So we don't know how the source evolves exactly from here to here, but the popularity of this model is that they can at least qualitatively explain many of the properties that we observe. So they explain the broadband spectral evolution. So this change from a hard X-ray dominant component to a thermal disk component dominating the soft band. They can explain the evolution of the variability, so how the spectra, the power spectra change, and they can explain the QPOs. Sorry. They can also explain QPOs, so quasi-periodic oscillation. However, there is no conclusive observational proof of how the disk evolves in between these two extreme states. Now, a challenge to these models is observation of broad iron K emission lines in the hard state. So basically, the Comptonized, so these features emerge because the Comptonized emission that we observe is also emitted back towards the disk, and here it is reprocessed. The way it is reprocessed is through thermal reprocessing. So these photons thermalize with the disk and they contribute to the soft thermal component, or they can be sort of reflected. So which means that they produce a complex spectrum, which is made of absorption, emission features, and Compton scattering components. So this is an example of this spectrum. What happens is that, so the most prominent feature is this iron K fluorescent line that is observed at 6.4 kV. And now the importance of this feature is that it is observed in a part of the spectrum which is quite clean from other components. So it is very easy to measure this line. And it is observed basically in all sources. So it's a proof of having a disk in this source. But the most important thing for us is the fact that this line, so the shape of the spectrum, and especially of this line, changes as a function of the position, the radius where this line is produced. So if the line is produced farther away from the black hole, then relativistic effects are not important. So the line is narrow. But when we approach the black hole, the line becomes broader and broader. And in a challenge to these truncated these models is that when we observe the hard state, especially the bright hard state, many of the sources show these broad iron lines. Now, if this broadening is due to relativistic effects, only to these relativistic effects, then the disk, it means that the disk must be close to the hard state. And so we have to review our modelization for these objects. Now, to address this problem, an alternative scenario that has been proposed recently is that the disk is depicted here. So according to this scenario, the disk doesn't evolve that much. So it reaches down to the innermost stable circular orbit quite early in the outburst. What changes most is the geometry of the hard X-ray source of this corona or hot flow. So this scenario can indeed explain the presence of broad iron lines in the hard state, because the inner part of the disk would be constantly illuminated during these phases of the outburst, and so it would produce this broad line. However, there is a lot of controversy regarding these measurements of broad iron lines. And this is nicely summarized in this plot. So these are basically measurements of the inner radius of the disk using reflection models. And these are done for the same source for different luminosities in the hard state, sometimes even for the same observation. And as you can see, these measurements are highly, they are not in agreement at all. And they also span a large range of values, like about 2 orders of magnitude. So this means that there is a large spread in the obtained values of the inner radius of the disk in the hard state using this reflection model. And this is due to the fact that these reflection models have a lot of parameters in them. So there is a lot of degeneracy. And this is also shown here in this work, where basically we fitted the spectra of MaxiJ1820, the new star spectra, with a reflection model. And what we found is that there is a huge chi-square barrier that divides the small radii solution from the large radii solution. What does it mean? It means that if you start your fits assuming a small radius, then it is very hard that trying refitting your spectra, it is very hard that you will be able to cross this barrier. So it's a lot of bias in the fits. It's a sort of bias in the fits. Okay, so it is clear from all this that we need an alternative method to try and break these degeneracies. And so we can use variability, X-ray variability. So X-ray variability is very important because not considering X-ray variability is like missing a part of the story, because it's what characterizes these sources. So it's important by itself, but we can use it also as a tool to understand these systems. So one thing that we can do is that studying X-ray variability at different temporal frequencies, different time scales, we can basically separate radiation coming from different regions of the disk. This is because the emitting regions that are farther from the black hole emit mostly slower variability. So the faster variability that is produced here cannot diffuse down to the black hole. So it's basically dumped where it is produced, which means that we can assume that the slower variability that is observed from this system comes from a larger radii, while the faster variability comes from smaller radii. So basically, when we observe the system, we extract a light curve. We have contribution from all these components. So fast and slow variability. So we can extract the light curve, take a time average spectra, and do our analysis. But we can also apply Fourier techniques and decompose these light curves into several components that would correspond to emission from different radii of the accretion flow. So studying these different components, we basically can extract spectra, so we can have an idea of what is the spectral shape of the component of the emission that comes from different radii from the black hole, different distances from the black hole. And the fact that we have variability allows us also to measure reverberation lags, which means that we can basically, if we have direct variable emission and then we have reflected emission, what happens is that this reflected component will reach the observer with a time delay due to the relative distances between the hard X-ray emitting region and the disk. So these distances are imprinted in the time delays that we can measure studying these light curves. And these time delays are directly related to relative distances and so to the geometry. So basically studying these reverberation lags, we can reconstruct the geometry of these systems. So X-ray reverberation is a powerful technique. There was first, the first reverberation measurements, X-ray reverberation measurements, were actually done studying AGN. This is like a technique, the reason is pretty technical, is due to the fact that the time scales for studying that are relevant for studying the inner regions in a supermassive black hole are longer. So we can collect more photons on the relevant time scale. So it is easier to make these studies in AGN. So the first detections date back to 2009 in AGN. So when we studied X-ray reverberation lags in AGN, what we found is that these lags scale with the black hole mass. And if we convert these time delays into distances, what we observe is that they map very short distances of the order of a few gravitational radii from the black hole. What does it mean? It means that these lags are produced very close to the black hole, so they are giving us, and they can be used as a tool to study these regions. And what is important is that they scale with the black hole mass, which is what we expect from reverberation lag. Because if this emission is produced always in the same region of the disk, if the size of the system increases, then the lag increases, and the size of the system increases with the black hole mass. So one expectation that we have is that the same lags should be observable also in black hole binary systems. So this relation here should scale down to black hole binaries. So this was actually possible. So thanks to the sensitivity of XMM Newton in the soft X-ray band, it was possible to measure the first evidence of X-ray reverberation in a black hole binary. The first study was done by Phil Apley on the black hole binary GX39-4. So this is a spectrum of time delays in different energy bands with respect to a common reference band. So basically, in previous studies, when we didn't have the coverage that XMM had, so in the soft band, studies were restricted to this part of the spectrum. So what it was observed is that the lags were hard, which means that harder photons were delayed with respect to softer photons. This is a very common feature in black hole binaries, and I will discuss it later, but it was observed, it's observed in any system. But what we would expect here is that if this, we would expect this trend to extend to the soft band. Instead, using XMM data, and looking at and extracting variability on very short time scales. These are the temporal frequencies that we are considering, so fraction of a second. This turnover was observed. So this turnover is telling us that the soft band, where the disk is observed in the hard state, is delayed with respect to the hard band, and is delayed by a few milliseconds. So this was taken as a first evidence that fast variability got in an imprint of this reverberation signal. So we were very interested in this. So what we did was to go through the XMM archive and look at all sources that were observed, and we searched for reverberation lag because we wanted to use it to map changes in geometry as a function of the accretion state. So what we did was we found evidences, more evidences or reverberation lags in this source, in other observations. And so these observations are all in the hard state for GX39-4. And as you see, there is what we observe is a scaling of the reverberation lag amplitude as a function of luminosity. This is telling us that as the source rises towards the bright hard state, the reverberation lag becomes shorter. This basically means that the relative distances are getting shorter. So this agrees with the scenario where the inner disk radius slowly approaches the innermost stable circular orbit as the source evolves throughout the hard state. We tried and looked for evidences of reverberation in other sources. In the XMM archive, we could find one only in this other source. Comparing it to GX39-4, it was again a source observed. Well, the reverberation was observed again in the hard state. Comparing it to GX39-4, it agreed with this trend, but the measurements were all at same when the observations were all taken at the same phase of the hard state, so similar luminosity. So there is not scaling that could be observed within this source. So basically, this sort of confirms the scenario, but is not enough. It's not enough because we want to know what happens in the other states if this reverberation lag can be used to trace evolution of geometry throughout the whole outburst. And so the data were insufficient. So they couldn't cover other phases of the outburst, especially the transition, which is a very fast phase of the outburst. So it happens very quickly. And this is because XMM Neutron was not designed to perform this kind of studies. First, because like pointing, so the pointing is quite slow. So if you give a trigger, it takes several days to point the telescope. And the other problem is that XMM cannot observe very bright sources. So this transition where everything happens, the jet disappears, the spectral properties changes, happens at very high luminosities. And XMM has limitations to observe very bright sources. So the conclusion is that we needed more data. Unfortunately, the Neutron Star Interior Composition Explorer, NICER, was launched a few years later, was put on board the International Space Station, and NICER is a powerful machine for this because it has 52 operative X-ray concentrators, and which are paired to silicon drift detectors. And this makes of NICER a very good instrument because it allows it to acquire a large effective area with very good fast timing capabilities, and most importantly, no limitations to observe these very bright sources. And luckily, after the launch of NICER, a very bright source went off. This is MAXI J1820. Many of you know it, heard about it. This is because it happened to be one of the brightest X-ray binaries ever observed. So it went into an outburst in 2018, And this outburst turned out to be a complete outburst, which means that the source went through all the evolution and then down again to the low luminosity hard state. And NICER could monitor it perfectly, very well. And this is like the hardness intensity diagram for this source made using only NICER observations. So as you see, there is a very good coverage of all the different phases of the outburst. Of course, this attracted the attention of all the community. So there is a lot of papers that have been published on this source. But for our goal, this is one of the most important papers. Basically, this source was studied to look for reverberation lags. And in this study, reverberation lags were reported for a few observations in the bright hard states. So this is another way of representing these lags. So basically, it's a plot of time delay as a function of temporal frequency. And the reverberation lag is basically this negative feature here. As you see, there is a clear evolution of this lag. So the lag, as the source moves in this direction towards softer states, the lag becomes shorter, increasingly shorter. But one of the main results, I think, regarding this source was instead came from the multi-wavelength study of this of MAXI J1820. So basically, this intensive monitoring of this source allowed for the first time to have a quasi-simultaneous observation of the multi-wavelength observation of the transition. So basically, X-ray and radio monitoring. So in the X-ray, what happened was that it was possible to observe how the power spectrum evolved. So basically, from a powerful from a power spectrum showing significant broadband variability plus some QPO, what it was observed that at the transition, this variability dropped and was substituted by a single very intense quasi-periodic oscillation. And this happens quasi-simultaneously with the detection, so with the launch of these of ballistic jet blobs. So these are radio images for this source. And this detection happened a few hours after the detection of this type QPO. So this was the first clear evidence that these two events in the X-ray band and in the radio are linked. So the X-ray source has a link to with the jet. So what we did was we decided to look into this observation more in detail. So to study them, to try and see how, if we could map the evolution of reverberation lags throughout this phase of the outburst up to the transition. So we studied all these observations. Here are some examples. Again, this is a plot of time delay as a function of temporal frequency. So what we observed was the first feature that is observed is this positive lag here. So these positive lags are hard lags, as I mentioned before. It means that the harder photons lag behind the softer photons. And this is something that is very common in black hole binaries, as I said. And the best model that explains these time delays is a model that, that invokes the production of, the propagation of perturbations in the mass accretion rate that are produced at different radii in the accretion flow. This produces variability over different time scales, but some of them diffuse down and can reach down to the innermost part. So this diffusion from the outer radii to the inner radii is what produces these hard delays, because the outer parts produce much more softer radiation. The inner parts produce more more harder variation. So this naturally produces a soft to hard time delay. So basically what I want to say here is that these legs are, in this scenario, are related to diffusion timescales in the accretion flow. However, these time delays depend on frequency and they go down in amplitude. So there is a point where they are not that dominant anymore. And here at high frequency, so which means very short time scales, what we observe is the emergence of these negative legs, which is what we ascribe to reverberation. So here the disk responds to the illumination from the hard X-ray source, producing these short time delays that we ascribe, what we explain as reverberation. Now, the most interesting stuff, however, happened at the transition. So this type of legs were observed throughout all the analyzed observation. But when we arrived at transition, what happened was that these hard legs here that are associated with the emitting primary continuum disappeared, and everything was replaced by a soft unique reverberation legs that dominated the overall time scale sampled. Now, how do we explain this? So we decided to try to sample this evolution in a more rigorous way. So we applied this spectral-timing model, which is called ReLTrans, to basically obtain a phenomenological description of the leg shape, of the leg profile. And we use this information to extract this frequency here, which is where the reverberation leg goes to zero. Okay, I don't want to go into the details of this, but basically we need this measurement because this is a less biased measurement of the intrinsic leg amplitude. So basically we measure this frequency, and then we plotted this frequency as a function of hardness. And what we observe is that this frequency increases as the hardness decreases. So as the source moves towards softer states, the hardness decreases. So as the source moves towards softer states, the frequency of the hard leg, the characteristic frequency of these soft legs, these reverberation legs, increases, which means that the intrinsic leg amplitude decreases because they are related inversely. So in this direction, the intrinsic leg amplitude decreases. So as the source goes to softer states, the amplitude of the reverberation legs is shorter, which means that there is a change in the geometry of the system. It means that the relative distances between the X-ray source and the region of production of reverberation legs in the disk gets reduced. However, when we got to the transition, what we observe is that this trend breaks. So the reverberation leg doesn't follow this trend anymore. So the frequency suddenly decreases, which corresponds to a sharp increase in the relative distance between this reprocessing region in the disk and the hard X-ray source. And what is interesting is that this happens just a few days before the ejection of these jet blobs. So we explained that in terms of changes in the hard X-ray source. So in the hard state, the main region of hard X-ray dissipation is located close to the black hole, while at transition, the region where dissipation occurs is likely associated with the jet. So this would explain the long reverberation lag, because if dissipation occurs in a region that is larger or more distant from the disk, then it would irradiate a larger region of the disk, and so it would produce longer legs. This scenario was independently proposed by other authors, and a few days ago, new paper was out that showed that this feature, so this long reverberation lag at transition, is present in other sources observed by NICE. However, what happens to the disk? So we went on with this analysis because we wanted to know what actually happens. So how the disk evolves. So we wanted to extract measurements of this disk radius. So what we did was to extract these spectra. These are covariant spectra. Basically, using these spectral-timing techniques, it is possible to, as I told you, to extract spectral emission from the isolate only the components that are producing the reverberation lag. So basically, this spectrum tells us which are the components that produce the lags. So in all these spectra, we observe the comptonization component and a disk thermal component. This is telling us that basically the comptonization component is what triggers variability, and the disk thermal component is what responds to this variability, producing these lags. So we measured this lag and we fitted them. And from these fits, we extracted constraints on the temperature of this thermal component, which is the part of the disk that responds to this fast variability. So we measured the disk inner temperature, and we plot it again as a function of hardness. And what we see is that the temperature of the disk where reprocessing occurs steadily increases as the source becomes softer, so as the source approaches transition. So it means that the disk becomes hotter and hotter, which is what you expect if the disk gets closer to the black hole. So from this measurement, it is possible to extract an estimate of the inner radius of the disk. So we did so, and we found that the inner radius of the disk, so basically the disk is results quite truncated at the beginning of the outburst and stays truncated for most of the outburst until it reaches transition. So at transition, it is consistent with reaching close to the innermost stable circular orbit. So trying to piece all this information together, we interpreted this as an evidence of an evolving inner disk radius throughout the entire hard state. So basically, when the outburst starts, the reverberation lags are longer and the temperature of the disk is lower. So the disk is colder. And this evolves steadily throughout the hard state. So it means that the disk becomes increasingly hotter and less truncated. However, at transition, while the disk becomes very hot, it keeps going through that trend that I showed of temperature, the lags become very long. So what we interpreted it as due to the fact that now dissipation occurs in a larger region, most probably associated with the jet. So in summary, we overviewed the behavior of black hole binaries. We addressed the problem of constraining geometry as a function of accretion state and how this can be done using spectral timing techniques. And I showed you results regarding Maxi J1820, where this study give evidence of the fact that the disk steadily evolves throughout the hard state, reaching close to the ICE-CSIC when the transition occurs. And this is closely linked to the ejection of this to ballistic jet ejection. And maybe we can conclude with some guidelines for the future of these kind of studies. So what do we need to perform these kind of studies? So of course we need high count rates, and for that we need large collecting area. So this was possible thanks to NICE that has this very large effective area in the soft band. And of course, this source, as I told you, can get very bright. So we need the capability to observe these very bright sources. Of course, we also need timing capabilities. We need to reach high time resolutions, and in order to perform simultaneous spectroscopy and fast timing. And we need flexibility. This is because this transition, as I told you, and maybe, and I hope I convinced you, is the most important phase of the outburst, probably, because it's where a lot of information we can get a lot of information about how the accretion flow evolves, but this happens on a very short time scale. So this transition in the case of Maxi J1820 occurred in a matter of a few hours. So we need flexibility. So we need to be able to point telescopes at the right moment to see this transition. And so we need fast reaction time. And then another important part is synergy with multi-wavelength facilities, which would allow us to perform this kind of studies of linking the properties of the jet to the hard X-ray source, for example. And I give you here some reference of a few papers where the authors put a lot of effort into applying fast timing techniques to infrared data. So it gives an idea of what can be done combining X-ray and infrared fast timing. So I think I will conclude with this slide here that gives a perspective of the future. So this is the effective area, the comparison of effective areas between the ICE-CSIC instrument on board XMM in ICER, which gave good improvement in the soft band, and then what is expected with a TINA XIFU. So this is a huge improvement because it's a factor of 10 in effective area, and you have to bear in mind that the sensitivity of lag measurements scale by the same factor. And another instrument that is foreseen, another facility that is foreseen for the future is EXTP, of course. And also EXTP will give a lot of improvement in this sense, because especially if we consider the iron K band, so where reflection is better seen because we have this isolated iron K line. And the improvement here is by a factor of 40, with a good improvement also in the soft band. So I'll stop here and thank you for your attention.
Thank you very much for this nice overview. Are there any questions from the audience? Yes.
Thank you very much for the very nice talk. I was wondering, with a better timing capability, is it possible to study from the lag, the early acceleration of the jet, and in this way to constrain the details of the jet emission, jet launching mechanism?
Before you answer this, could you just repeat the question so that people online can hear it?
Okay. So I was asked if with better timing capability, is it possible to constrain the time of jet ejections?
No, to track like the acceleration of the early acceleration.
The early acceleration, yes.
And constrain the jet launching mechanism.
Yeah, okay. So this is done basically in the radio band. Okay, I didn't put a picture here, but basically what is, I can show you this. Where is it? Okay, it doesn't appear because it's a transition. Okay, here. Okay. So basically, by monitoring this ejecta, is it possible to trace them back to the launching moment and reconstruct the acceleration curve, so the velocity curve, and then get the acceleration. So this is something that is done when you can resolve these blobs. So you need the radio band basically. So it has been done also with Chandra. So some of these ejecta were seen with Chandra. But of course you need imaging power for that.
Okay, any more questions? Anyone online have a question? You can also write them in the chat and then I can read them out. And while that is happening, I might have another question. So this might be a naive question, but are you able to like actually like constrain masses of these black holes in some way? Or like, is there some like correlation between the different phenomena that you have on that slide and the actual mass of the black hole?
Yes. Yes. So, for example, reverberation lag depend on the mass of the black hole. So if you know what happens to the if you know where the lag is produced, then you break this degeneracy between the radius of emission and the black hole mass. So you can constrain the mass.
Mm-hmm.
So yes, there is
but it's not like the like how often you see like actually these features like depend on the mass. Like for example, heavier black holes go into outburst more often. You see these kind of like features more often.
I don't think there is. I don't know. Well, okay. You mean like a sort of correlation among the outburst?
For example, yeah.
No, I don't know about that. But the other problem is that these sources are likely to span a quite small range of masses.
Okay.
So if you want to measure any difference, you really need a lot of sensitivity to do.
Okay. Any other final questions? Yes.
Thanks for the nice talk. Something that always I've never been convinced about this source is that when you transition to a soft state, there is this moment when it declines and then it goes back. I was spotlighting that it's the bright decline phase at some point in the hard to soft transition.
Do you mean the lag? Like
in general, like the fact that at some point.
Okay. Yes.
I was wondering if, because with spectral we could not find any reason for that.
You mean this one?
Yes, exactly. Like the pink and then green part. I was wondering if.
Good question.
Spectral-timing techniques can tell us something about what's going on, because I don't think it's very common. I mean,
I know it's seen also in GX39-4 in an outburst where a source was did the transition at low luminosity, 2004, and but from a timing point of view, I didn't look into it, but it's true that. Okay, if you look at the lags, there is no clear difference. But if you look at the temperature that is measured, there is a sort of pattern here. So a wiggle, you see, a wiggle here. So maybe can say something, but so it's like if the temperature changes its trend, so something changes in the configuration of the disk. But no, but it's interesting.
Okay. If there are no more questions, let's thank Barbara again. Thank you very much. Now there should be pizza outside for everyone.
People